All right, so first we're going to talk about probability. We need to know what probability is. So when we talk about probability, it's just the likelihood of an event occurring. How likely is it that it will rain today? How likely is it that you'll get an A on your next test? How likely is it that something happens? That's a probability. You guys have probably done a little bit with probability before. Did you maybe get to some in Algebra 2 a little bit? Maybe a little before the EOC. It shows up, there's a lot on the ACT. They like to do some probability questions. One thing to keep in mind, the probability is not a guaranteed thing. If I flip a coin, what's the probability of getting a heads when I flip a coin?
50%.
50%. Everybody agrees with that. Does that mean if I flip the coin 4 times, I will get 2 heads?
No.
No. So we know probability is how likely something is to happen, but there's a difference in what we expect and what we sometimes see. Now, if I keep flipping that coin, if I flipped it 10,000 times, do you think it would be closer to half of them heads and half of them tails? Yes. So the more times you repeat it, the more likely it is that what we see is close to what we expect. So that's what's called the law of large numbers. As the number of trials increases, as I flip my coin more times, my real probability should get closer to what I expect. A sample space, we use a capital S for that. That's every possible outcome. When I flip a coin, what's my possible outcomes? Head or tail. Okay, if I flip a coin twice, what would be my possible outcome? We could get, like for the 2 flips, I could get a heads and a heads, or a heads and a tails, or a tails and then a heads, or 2 tails, right? So sample space lists everything that can happen when we look at our experiment. When I'm talking about an event, that's just a collection of outcomes. And we're going to do some examples to really illustrate what these terms mean in just a second. Here's our example. Let's consider a probability experiment of having 2 children. Okay, so part A, identify the outcomes. If I'm talking about gender, what are the 2 possible outcomes when I have a child?
Boy or girl.
Boy or girl. Okay, we're just going to abbreviate E and G. So the sample space is every possible outcome when we have 2 children. So it could be I have a boy and then another boy. Or we could have a boy first and then a girl next. Or a girl and then a boy, or 2 girls. So that's every combination I could get when we look at 2 children. If I said the event E is having 1 boy, which of these events in my sample space would match that description, having 1 boy? We could have boy, girl, or we could have girl, boy. There are 2 of my 4 possible outcomes where we have 1 boy. So do you guys kind of understand what I mean when I say an outcome, a sample space, and an event from that? All right, we have a few more rules, or a few more definitions. Sorry, beginning of a chapter, we always have a lot of definition. When we're talking about probability, there's two rules that have to be followed. What is the highest a probability could ever be? 1, 100% chance. What's the lowest? 0. So probabilities always have to fall between 0 and 1. And if you want to abbreviate, you really just need the highlighted thing. And the sum of all the probabilities always has to equal 1. When I add up all the probability of each possible outcome, the total has to be 100%. So every individual probability is between 0 and 1. Total probabilities add to 1. Probability models here. And so in a probability model, you list every outcome. So every possible outcome and its probability. So it will be like a table. We list what can happen and the probability of each thing happening. When something is impossible, what do you think the probability is? 0. If it cannot happen, it has a probability of 0. If it is certain, that means it will for sure happen, what would be the probability? 1. So if something has a probability of 1, it is a certainty. There is no other option. There is a 100% chance that this is the case. Unusual is just a low probability. It kind of varies depending on our situation, but for us, anything with a probability of less than 5% we'll call unusual. That means it can happen, but it probably doesn't. So less than 5% is unusual. So I want to make an example of a probability model. Several of your homework questions are going to give you probability models and say, is this a true probability model? And we're checking if the conditions are met. Conditions being that every probability has to be between 0 and 1. And when you add up all probabilities, it has to equal 1. So in a probability model, we will list each outcome and then the probability of that outcome occurring. And we'll just set it up in a table. All right, so we have a bag of 100 M&Ms. We have 12 brown, 15 yellow, 12 red, 23 orange, 23 blue, and 15 green. So a probability model, you just list the outcome and the probability. My outcome is my color. I'm just going to make a table with the color and the probability. You can list these colors in any order you want. I'll just go in the order of the problem. So the possible colors were brown, yellow, red, orange, blue, and green. So then the probability. What would be the probability of a brown imminent? 12 out of 100 or 0.12. In general, I don't care if you give me a fraction or a decimal. If you give me a fraction, please make sure it's in lowest terms. Decimals are fine, but you want to be a little cautious. If it's a big, nasty repeating decimal, I'd rather you not round it, so keep it as a fraction in that case. Yellow. Probability of a yellow would be 15 out of 100 or 0.15. Red, there are 12 reds, so 12 out of 100 is 0.12. 23 oranges, so 23 out of 100 is 0.23. 23 blues, so 0.23, and 15 greens. If you just put these decimals for your probability, that's fine. You don't have to have the fraction equals a decimal. I'm just trying to show you where I got them. So quick check to verify this is a probability model. If you add all those together, what should we get? 1. See if it works out. It works. Every probability is between 0 and 1. The total is 1, so it is a probability model. All right. So we calculated these probabilities just by dividing. The number of times it occurred divided by the total. And do you guys know that part about probability? You've done that part before probably. So there are 3 different ways to calculate probability. There's empirical, classical, and subjective. So these should be, let me check, our last terms for the day. Okay, so an empirical probability. If you look at your formula sheet, it kind of tells you, it says empirical probability is the frequency divided by the number of trials. That's what we just did. So empirical probability is based off a certain situation. Let me say a specific situation. So, for example, I flip a coin 10 times and get 1 heads. So the probability of heads would be what? Right, 1/10 or 0.1. It's based off what actually happened. Classical probability. So when you look at classical on your formula sheet, it says the number of ways it can occur divided by the number of possible outcomes. Okay, so in flipping a coin, it's not based off what actually happened, it's more what I would expect. So classical probability, this is, think of it as your expected probability. So my example, if I flip a coin, shorthand for probability, we can put P and then whatever outcome. So the probability of getting ahead when you flip the coin would be what? 0.5 or 1/2. So you notice these were not the same. Okay, empirical is what actually did happen. Classical is what I would expect to happen. So if you have real life data you're looking at, that's empirical. The final type is subjective. And that one is based on personal opinion. It is not on your formula sheet. So subjective would be like the weather. Does every single forecaster predict the same chance of rain today? No. Why? Because it's not that concrete. They have to take into account all these variables and try to guess, based on their personal opinion, what the probability of rain is. It might be like if I'm saying, well, based on how my students have done in the past, I expect the average test score to be an 85%. Is that actual data, like right now I'm taking your average test scores? No, it's based on my personal experience and it's my opinion. So subjective, something like the weather. You know, sports analysts, when they try to predict the odds that somebody's going to win a game, that's all subjective. It's kind of based on their personal opinion. Now they're basing it off something. It's not just a totally made up number, but different people might look at it and have a different answer for that situation. All right, so now let's just do a few more probability examples and then I will be done for today. So you don't have to write down the whole example if you don't want to. An insurance agent insures 182 drivers. So we have 182 drivers. Last year, 24 had to file a claim. Based on this, what is the probability a team would file a claim? So how would I find that probability? 24 divided by 182, the number that filed a claim out of the total. You can give me a fraction in lowest form. If you do give me a decimal, I ask that you keep at least 4 decimal places on it. A lot of times these probabilities aren't going to come out pretty. So if you give me that decimal form, 4 decimal places is sufficient. So there's about a 13% chance it would file a claim. Which of the 3 types of probability is this? This is empirical. It's based off something that actually happened. All right. Is that one okay with everybody? All right. Has anybody ever played Pass the Pigs? Oh, I might have to bring that in. It's a very fun game. You roll pigs, and depending on how they land, you score points. So, 52 students are playing Pass the Pigs. I've given you all the outcomes and the frequencies. If I want a probability model, so probability model, we have the outcome and the probability. Okay. How would I find the probability of each of these things? We have to first get our total, right? I didn't tell you how many times we rolled. So we have to add all these up to get our grand total. Okay, so then to get each individual probability, what would you do? Yep, the frequency divided by this. So 1344 divided by 3939. And we'll just go to 4 decimal places because this is not going to be a pretty fraction or anything. 1294 when we're rounding like this, is it guaranteed that all the probabilities will add up to 1 exactly? No, because we do have slight rounding error, but it should be very, very close. So does everyone understand how to get the probability model from this? And if I asked you to verify that it was a probability model, you would just say every probability is between 0 and 1, and they add up to 1. These do add up perfectly. See, we're just that good. So if you have a probability model, it's easy to answer some questions. If I said to estimate the probability that a pig lands side with a dot. So side with a dot, what's the probability of that? So I don't care if you tell me 0.3285 or you can say 32.85%. Either one is okay there. C, would it be unusual to throw a leaning jowler? What constitutes unusual?
Less than 5%.
Okay, what's the probability of a leaning jowler?
0.8%.
That is a 0.81%. So that is unusual. Are there any impossible events? What does it take to be impossible? A probability of 0. So nothing's impossible here. All right. Is this okay? Let's do just a couple more. I want to make sure I leave you some time to start homework, but all right. I'm not going to do this one because we already did one with the colors of M&Ms. Could you guys do that? That and all? Okay. How about, let's do this one. All right, you can tell I used a textbook to install these because the names are Yolanda. How many people have you ever met named Yolanda? So, Sophia has 3 tickets to a concert, but Yolanda, Michael, Kevin, and Marissa all want to go with her. To be fair, she randomly selects the 2 people that can go with her. So, determine the sample space. The sample space is a list of all possible outcomes. Okay, so my sample. I could pick, let's abbreviate these. So, let's do Yolanda is a Y, Michael is M-I, Kevin is K, Marissa will be M-A. So tell me every possible combination of 2 people we could pick. It's the same. So order doesn't matter on this because it's not like we're going to line them up in order or anything. I'm just taking 2 of you. So that's every possible combination with Yolanda. So then we could have
Michael, Kevin,
and that's every possible combination. All right. So if I want the probability of Michael and Kevin, so how many total outcomes do we have? 6. So my grand total is 6. How many of those are Michael and Kevin? 1. So there's a 1/6 chance that those 2 get to go. What if I want the probability that Marissa attends? So there's still just 6 possible outcomes. How many of them include Marissa? So be a 3 and 6, or 1/2, or 0.5. All right. Interpret the probability in part C. So interpret, that's telling me what it means. So So 1/2 is 0.5, so there is a 50% chance Marissa is selected. Is that okay? Last problem, I just want to do one to illustrate the difference between empirical and classical. Sometimes people get the two of those confused. So this is my very last one. So a survey asked 500 families with 3 children the gender of their children. It was found 180 families had 2 boys and 1 girl. So the empirical method is based off what actually happened. So if I want the probability of having 2 boys and 1 girl using the empirical method, what would it be? Let's do 180 divided by 500. You get 0.36. So based off the families I looked at, there was a 36% chance of 2 boys and 1 girl. All right, let's find the probability using the classical method. Bless you. So for classical method, this is our expected probability. So we would have to list out our sample space, every combination of 3 children. So boy, 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 girl, boy, girl, boy, so forth. Does that make sense? You can list them out like that, how we've done our sample spaces. You can also draw what's called a tree diagram if you want to. So I'll show you that. I don't really care which way you use it. This is just another tool. So if we look at our first option, when we have the first child, we get 2 options. It's either a boy or a girl, right? So I'm just using this to calculate all the possibilities. So that's the first child. Then for the second child, you can have a boy or a girl. So from here, this could be a boy or a girl. This one could be a boy or a girl. Okay, and then we did a third child. So again, boy or girl. This final column is essentially how many possibilities we have. As you can see, to get to here, it required boy, boy, boy. To get this one, you had to have boy, boy, girl. Boy, girl, boy. Do you guys see how we're getting this? So how many outcomes are there? 8 total outcomes. And I want to know which ones are 2 boys and 1 girl. So we could have gone the boy, boy, girl path, or the boy, girl, boy path, or girl, boy, boy path, and that's the only option for 2 boys and 1 girl. So how many of those did we have? 3. So we get 3 eighths, or what is that as a decimal? 0.375. Were these the same? No. So that's the difference between empirical and classical. Empirical is based off real data, what I saw happen. Classical is what I would expect to happen. Does that make sense to everyone? Okay. So I am done. The homework. Pay close attention to my directions here. So there are a lot of these questions that will say find and interpret the probability. I am not going to make you interpret, so you can just find the probability. I think there's only one question that you actually have to interpret, and I think it's 27 because it's 2 separate questions. Part A is find the probability, part B is interpret the probability. So on that one I want you to do the interpretation. But like 29 on, they're all saying find and interpret, and you don't have to do the interpret on those unless you really want to. Does everybody kind of understand those directions?
Which one do we have to interpret on?
27, like it's 2 separate questions. Like part A is find it, part B is interpret it. So do that